Hello, everybody. Um, I'm gonna cover the simulation of a cantilever beam um, that has two beams attached to the structure and a load at the tip. So please reference the document on the shape. And we're gonna use a frequency domain analysis. I'm gonna start sharing my screen. Okay, so we're gonna do a 3D simulation. I'm gonna start with the stationary. Um, and once we define the geometry, we're gonna select micrometers on this one. I'm gonna load some initial parameters. The length of the cantilever beam is gonna be 100 micrometers. I can write micrometers as U. This is the length. My parameter A, that is the width of the cantilever. Right now, it's going to be 5 micrometers. 4 micrometers. My parameter B is going to be 1 micrometer. This is the thickness of the beam. And we are going to define my, I'm gonna add, first save this one. This is AFM peak version 2. And I'm gonna add, right click here. I'm gonna add the variable, and the variable is gonna be my force input. And I'm gonna start with 1 micronewton. 1 micronewton for input force, okay? So I'm going here to geometry, where I select micrometer. I'm going to create a work plane. And on this XY work plane, I'm gonna start adding some rectangles. So the first beam is gonna be L in. Sorry, the height is gonna be I, and the length is gonna be L in. I'm gonna build selected. Let's make it a long beam starting from 0. And this is gonna be corner 0, 0. I'm gonna add another rectangle, and it's exactly the same, A as an L in, that's the length. But this time, oh, I forgot to add the mass of the beam. So I'm gonna use side. The mass is gonna be 25 micrometers. It's gonna be 25 micrometers inside. And I'm gonna move this beam, the second beam, I'm gonna move it in X, the side of the beam minus the A, minus 1 thickness here. So in this way, we're gonna have the 2 parallel beams sustaining the tip of the cantilever. And we're gonna add another rectangle that is going to be the mass side and side. It's a square side by side, but I'm gonna move it to the front. So I'm gonna move it in Y, the distance of L in. So at this point, we have this cantilever beam, 2 beams, and a mass on the tip. And I'm gonna go back to work plane, and I'm gonna say extrude, and the extrusion is gonna be B, thickness B. So now, right now, those are the 5 microns. I forgot to add on the beginning the study. So the physics that we're gonna simulate. So I'm gonna add a multi-physics. Add the physics. I'm gonna add the physics, and I'm gonna hit solid mechanic. And on this solid mechanic is compressing all the multiplicity. Now, the material that we're gonna use, I'm gonna select material, I'm gonna add a material, and on this material, I'm gonna select the MEMS and the semiconductors, and I'm gonna select the polysilicon for this material. Automatically, the polysilicon is giving us a Young modulus of 160 gigapascals and a density of 2320. So having each beam, because of these dimensions, we have calculated offline that the stiffness of the beam is going to be 0.2, and this other beam is going to have a stiffness of 0.2, so the combined stiffness is going to be 0.4. Those are two springs that are added in parallel. On the solid mechanics, I'm going to add some fixed constraints. Basically, this tip and this tip are going to be fixed. And I'm going to add a load. So I'm going to do a volumetric forces, volumetric load, and I'm going to apply in this one my total force. So the units is in Newton, and I'm going to be minus F in. This is my initial input. Okay. Now, let's evaluate the damping factor. Well, the damping, we're going to add it later on. Let's simulate this study right now. So let's do the mesh, let's build all, and then the study that is going to be stationary, and let's hit compute. This one's doing well. And under the stress volume, please go to deformation, and the scale factor is going to be 1. So we know that what we are plotting here, it's effectively this deformation. And because we are interested in knowing what is the deflection, we're gonna do 1D plot of the solution, and we're gonna add a point graph. And in fact, I'm gonna use the deflection of this point here, the deflection at the end of the beam, so we don't consider the deflection of the mass. And we're gonna plot. And the deflection of the beam is gonna be around 3 microns for that size with that input. Now, if we want to do the time domain, I'm gonna, without the damping, let's do a study. Sorry, I'm gonna do the frequency domain. So not the time domain. And so I'm going to study, and I'm gonna add a study. And the study that I'm gonna be doing is the frequency domain. Okay. Let's select here, instead of the step, let's change to logarithmic. And we know that this is in the kilohertz range. So I'm gonna do it between 1 hertz and stop in 100 kilohertz in steps per decade. Let's do 10 steps per decade. And let's compute. So let's compute everything here. Because at this point, we don't have any damping coefficient, the solution of this should be an oscillation. And that's the problem. So I'm going to, because there is nothing reducing the energy on the system. So if I go to results and I do 1D and I right click the point graph, and again, I'm gonna point this one here, and I plot, I'm gonna do the solution 2, that is the frequency domain, and I do the point. What we are observing right now is that there is a huge spike, let's do logarithmic scale in X. And you're gonna see that there is a huge spike due to the resonance frequency at a frequency that is around this is gonna be kilohertz, 10 kilohertz, 20, like around 60 kilohertz. 60 kilohertz, that's gonna be the resonance frequency. Sorry, 1, 2, 3, 4, 5, like 50 kilohertz. This is gonna be the resonance frequency. And it's huge because there is no damping. Okay. So if we do the time analysis for this, let me add another analysis. So study, and let's do in microhertz, in microseconds. So I'm gonna do a time dependent, and I'm gonna do it in microseconds. And I'm gonna do up to 100 microseconds with 1 point. And I compute this time analysis. You're gonna find out that the simulation is a sinusoidal wave because there is no damping at all. Now I'm gonna save this file and I'm gonna make another file. I'm gonna save this as a no damping, and now I'm gonna add the damping, and I'm gonna show you how to add damping, hopefully seeing the critically damp and over damp and under damp. Okay, so now I can add a plot, 1D plot. This is the third solution, and now I'm gonna add the point graph. Again, let's do it again, the same point at the end of the beam. And as I predicted, this is an oscillatory time and an oscillatory response because there was no damping at all. So now you have frequency response. Sorry, you have the stationary response. It was a 3 micron displacement with 1 micronewton. I have the frequency response that is predicting resonance frequency at around 50 kilohertz and around 60 kilohertz. And I have the time response because there is no damping on the system. This is going to be oscillating. So I'm going to record another video now changing these values and doing with a damping coefficient.